Welcome to the Arefco Service Group YouTube channel. Please remember to subscribe and ring that bell to get notified whenever we upload a new video. To properly explain the basics of three-phase electricity, we have to start at the beginning. Power is produced at a power plant. It may be a coal-fired plant, a natural gas plant, nuclear or hydroelectric dam, a wind turbine, or solar facility. The electricity is transmitted from the power plant using these high-powered transmission towers. We've all seen these towers. Their job is to take the electricity from where it is produced to a substation. These substations can be scattered all around a city or a county, and electricity is either split off to another substation or distributed directly to your home or business. However, before it can go into your home, it needs to be converted from three-phase electricity to split single-phase and reduced from 7,200 volts to 240 volts. CAN transformers are quite common in the city and are usually mounted on utility poles. Can be mounted on the ground, oftentimes in the suburbs. The power from the substation coming into this transformer is 7,200 volts. The electricity is then split off to 4 or 5 different homes or businesses. In most cases, the electricity going into a home is 200 amps at 240 volts. To give you an idea of how much power that is, let's do a little math. Going back to Watt's law, if we multiply amps times voltage, we get watts. 200 amps times 240 volts equals 48,000 watts of power. Approximately 746 watts equals 1 horsepower. By dividing 48,000 by 746 equals about 65 horsepower, which is about the same as there is in a modern smart car. If you think about it, that's quite a bit of power. But just because it's available, that doesn't mean your house uses that much power all the time. Coming into a house, there are 3 wires. 2 are insulated and 1 is bare. L1 and L2 are insulated and the neutral is bare. On the right, we have the CAN transformer with 7,200 volts on one side, and that is split off like we see in the schematic. If we measure the voltage, we can see there's 120 volts between L1 and neutral, 120 volts between L2 and neutral, and between L1 and L2 is 240 volts. So where does phase come into all of this? Let's look at the phase between L1 and neutral. As we talked about in the video Basic Electricity, alternating current flows in both directions. It flows back and forth 60 times a second. The generator at the power station is pushing and pulling the electricity back and forth, and it does it 60 times per second. But for this illustration, let's say it cycles at 1 cycle per second. The black wavy line is called a sine wave. It shows how much push and pull is present as electricity alternates back and forth. It starts on the left at 0 volts, it quickly climbs to 120 volts, then alternates back down through 0 volts to 120 volts again. The generator at the power station does this push-pull 60 times per second. So let's look at the phase between L2 and neutral. Now let's look at our electricity between L1 and L2. If we add both phases together, we get 240 volts alternating like this. We'll get back to sine waves in a moment, but let's look at a simple generator. As you know, magnets have a north pole and a south pole. In our generator, on the top magnet, the pole facing the center of our generator is north on the magnet. On the bottom magnet has the south pole facing the center of the generator. The stator, or the center of the generator, also has 2 poles. The top of it is north and the bottom is south. As you can see, the poles are facing each other. Like poles repel and opposite poles attract. Our generator rotates like this. As it rotates, and the stator is in the position it is now, with the poles facing each other, the electricity is going to be pushed. With neither pole facing each other, there is no electricity being generated, so we'll start at 0 volts. As the stator rotates, The like poles pass each other and we get a push in electricity, and as it continues back to facing neither pole, the electricity falls back to zero. As the stator rotated, we now have like poles facing each other, and the electricity is going to be pushed toward the negative as it continues to rotate until no pole is facing. So the electricity goes back to zero again. This completes one cycle when the center goes back to its original position. The problem with a generator like this: building a generator large enough to power a city would shake itself apart if it were set up as a single-phase generator. The stresses caused by the back and forth motion of the electricity would cause too much vibration. The other problem is you only have so much usable electricity. As you can see, up at the top and the bottom, that's where our usable electricity is. The rest of the time, it's just not producing enough usable electricity. So let's go back to this again, only this time, let's see if we can provide even more electricity and eliminate the stresses on the generator. For three-phase electricity to be generated, we need to add some parts to our generator. We're going to add two more parts to the center section, and we will have three magnetic sources of electricity. As they rotate, they're going to create additional sine waves or sources of electricity. The black magnet is represented by the sine wave on the left, but now we're going to generate two additional sources of electricity. Okay, so let's get rid of this generator and look just at the sine waves. The black phase is shown here. Now let's put in the red phase. Notice that they are 120 degrees apart. Now we'll add the blue phase, and again, 120 degrees behind the red phase. We have three distinct sine waves, each one producing electricity and giving us a more constant flow of electricity. And you can see at the top and the bottom, there is a more constant flow of usable electricity. The three phases overlap each other, so the level of electricity supplied remains constant. Three-phase power is preferred by electric companies because it allows for certain benefits not attainable through other delivery methods. There is no need for a neutral line in a three-phase delivery system. This is because each of the three phases is carrying the exact same amount of current, which results in a linear balanced load. This allows the generators to work with more efficiency and less vibration. Three-phase power supply requires less conductors or wire material than single or split-phase delivery systems. The same amount of electricity can be delivered in a much more economical fashion. So how does this compare to house wiring? There are two types of three-phase wiring, delta and Y. We are looking at a delta system. Oftentimes, a neutral is added to the system to allow for single-phase delivery for lights and other low-voltage equipment. So let's take our voltmeter here and measure between our phases. Between L1 and neutral, we have 120 volts. Between L2 and neutral, we have 120 volts. And between L3 and neutral, we have 120 volts. Between L1 and L2, we have 240 volts. Between L2 and L3, we have 240 volts. And between L1 and L3, we have 240 volts. Three-phase power is delivered at much higher voltages. You can also get it in 460 or 480 volt configurations, which can also split off into 208 volt, 208 volts, or 277. There's a wide variety of combinations that we can make to get different voltages for different purposes. So this is why three-phase power is used. This is the basics of how it's produced and the basics of how it looks compared to household voltage.